Okay? So let's see, if I have an angle, I want you to draw the vector first. Okay, so I have an angle that is, or I have a vector that's 30 newtons at 42 degrees north of east. I want you to draw that vector, and then we're going to start breaking down the components of it. North of east. Okay, do we need to review how to draw it, or do you want to try it by yourself? So always start with your origin, with your crosshairs. Okay. Then we first draw our kind of basic, bland vector, right? And generally this vector needs to go in what direction? Generally up and to the right, okay, northeast. So it needs to go up here somewhere. Okay? So now we have to decide, we want our vector to be north of east. So we need an angle. Our 42 degree angle needs to go either here touching the origin or here touching the origin.
The right one.
Okay, on top of the angle or on the bottom?
Bottom.
On the bottom of that vector. Okay, and so that means we're 42 degrees right here. And the way we know that is because we want our angle to touch which axes? The east, north, south, or west? We want our angle to touch that east axis. Okay, because it says it's north of east. So we say it's touching the east axis, then we decide, does our vector go north of east or south of east? And it goes north of east, so this matches. Okay, we build our triangle around that angle. Now let's find these components. So I have the hypotenuse, which is equal to 30. Yeah, 30 newtons. So how can I go about solving for this y side? Opposite over hypotenuse. Good. So we would say 30 equals, not equals, sorry. 30 times sine of 42. Okay, do you remember that notation? That's how we write that. Okay, it just takes out one step. If you wrote it out the long way, it would look like this. Sine of 42 equals y over 30. Okay, all we're doing is multiplying those together ahead of time. Make sure your calculator is in degrees, not radians. Okay. What do we get for the y component here? 20.1. And what's our units for the component? Still newtons. Yeah, it's got to be the component, right? You can't make up a whole of something without parts that have the same units. Okay, so when we solve for our x component, we're going to take the hypotenuse times sine or cosine? Cosine, good, of 42. And shouldn't it be pretty close to 20.1?
Yes.
Should be pretty close. Not exact, because it's not a 45 degree angle, but it's pretty close. Okay, so we should get a little bit bigger number. 22.3 newtons. Okay, are either of those components negative? No, because we're going north and east. That's really important. Let's say that I apply a force of 68 newtons at 31 degrees west of south. West of south this time. So always start with your crosshairs. And as we do this enough, you'll start to just be able to think, okay, west of south, that means I need to start south and move west. That's where my angle needs to go. So it'll get quicker as we do this more often. But we're going to start with a basic angle in that direction. We want it to touch the south axis and swing to the west, which means my triangle should look something like this. Okay, and my 31 degrees goes right in here. West of south. West of south. Okay, so we're going to go straight south, then we're going to swing to the west. Did everyone get this on their own? Good, good. And what's our hypotenuse here? 68 newtons. Good, so let's go ahead and solve for y and x. Okay, we'll solve for x first. To solve for x, are we going to use sine or cosine? No, look. Sine. X is not always cosine. We cannot get into that habit. That's not something that you can remember. You have to look at your triangle every time. Almost every physics class I have tries to do that, but it's not the case. Okay, for half of the angles it's the case. For half the other angles it's not the case. Okay, so just look at your triangle. X is going to be sine, so we'll take 68 times sine of 31. And for y, this time we would use cosine, so we'd say 68 times cosine of 31. So x, you said we got 35.02. Okay, I'll just keep it at a whole number, that's fine. And then for the y value, what did we get? Okay, is that it? That all we need? No. Which directions are we going? Negative, negative. Okay, we're going south and west. That tells you that both of your components have to be negative. I'm telling you, if you do not take the time to go back and check with that, you're going to waste a lot of time doing problems wrong. Okay? Think about that. Think about if we have 4 vectors that we want to add together, and on your first one you forget a negative. That means everything you did past that point is almost wrong, right? When you get to the resultant part, it's not going to be right. You have to make sure you take the time to go back and check for those negatives. Okay, our units here would be newtons as well. We're going to start putting these 2-dimensional vectors into our free body diagrams now. Okay, now it gets a little bit more fun. Okay, so I'm going to try, I'll write down an example problem here. Okay, said a rope is pulling a 24-kilogram box with a force of 50 newtons at 62 degrees to the horizontal. And then we're going to find out what is the normal force. Okay, this is my box, right? I'm pulling it at an angle. Do we see at least visualizing what's happening? It's kind of like you're dragging something, right? From your standing position, that box is on the ground. Okay, so that's just overall what that system looks like. We're going to scale it down to draw the free body diagram. Okay, so let's think about all the forces that are acting in this system. Okay, we're not going to worry about friction. Okay, so let's scale it down. Here's my box. We know I've got this applied force that's going up at an angle. When it says to the horizontal, that means north of east. It means from the regular horizontal axes. Okay, from that positive horizontal axis up from that. So to the horizontal means north of east. Okay, and we'll say that a lot. And sometimes it even leaves out the to the horizontal part and it just gives you the angle. That means we're just using our regular, basically upward from that positive axis, okay? But it means to the north of east. So I've got my applied force of 50 newtons. What other forces do I have acting on this box if I don't have friction? Gravity. Good, and gravity goes where? Straight down. The normal force goes where? Okay. So it says we want to calculate the normal force. In this situation, is the normal force going to be equal to the gravitational force? No. Okay? And the reason is because as you're pulling this box upward, you're not necessarily lifting off the ground, but you're taking some of that pressure off the normal force. You're relieving some of that pressure. In order to do that, the first thing we have to do is break down this vector. Okay, we don't deal with forces at angles, right? We have to break them down into the components. Okay, so my angle here, 62 degrees, fits right in here. All right, and if my angle is applied, I'm going to label this force applied. So then when I solve for this side, what would I maybe call this side? If this is all force applied, what would I call this side? Force applied y. And force applied x, right? We're finding the x and the y components of that applied force. Okay? What's really important to remember is that once we break down this vector into its x and its y components, we don't use that 50 again. Okay? We won't use that again. Right, break down this vector in f applied y. We take 50 times sine of 62, making sure that your calculator is in degrees. Okay, tell me what we got for the y component. 44.1, okay. And for the x component, we got 23.5. Should either of those components be negative? No. So I'm going to go ahead and just put these in here so we can see them. 44.1 and x was 23.5. All right, we are solving for the normal force. The normal force, is it vertical or horizontal? Vertical. So do we care really about our horizontal forces right now? No. Okay. So now let's move on to setting up our net force equation. And we're looking only at the net force in the vertical direction. So I'll just put a little y there so we remember. You don't have to include that, but you can. We're solving for the normal force, which means we're only looking at vertical forces. How many vertical forces do we have? 3. 1, 2, 3. So how many upward forces do we have?
2.
Okay, normal plus F applied y minus FG. Okay? So now, let's think about this. Is our object accelerating in the vertical direction? No, it's just sliding horizontally. It's not moving up and down at all. So that means our acceleration in the vertical direction is 0. So our net force is 0. Okay, in the vertical direction. We're solving for our normal force. Do we know what F applied y is? Yes, we do. And it is 44.1. Fg is equal to mass times 9.8. So I'm going to plug in here 24 times 9.8. Okay, so I'm going to take 41 minus 235.2. So I get 0 equals normal force minus 191.1. To solve for normal force, all we do is add that to the other side. So our normal force is equal to 191.1 newtons. So, does that match what we expected? Did we expect the normal force to be lower?
Yeah.
Didn't we say we were taking some pressure off the normal force? So it's lower. Okay? What if I applied a force in the downward direction? Yeah, what if I just pushed on the table like this? Would my normal force increase?
Yes.
Yeah, it would increase, right? I'm exerting a downward force, so I'm working with gravity, right? I'm increasing basically the weight of that for a little bit, which means the floor has to increase its upward force. Yep. So if we pushed at it at an angle, we'd have a downward force at an angle. Our components would be different. We would have an increase in the normal force. A 100 kilogram table Okay, let's get this written down. I'm hearing too much talking. So I have a 100 kilogram table. I apply a force of 90 newtons downward. What's the normal force? So we've got gravity here. We've got our normal force. So does our downward force look like this?
No.
No, why not? Yeah, exactly. You're working with gravity, and we always draw our vectors away from the system. Yeah, away from the origin. Okay? So now our applied force is 90 newtons. Now we have to draw our components. Right? And it's 45 degrees, so it didn't even really matter which side of that vector we drew it on. Does that make sense? We could have drawn it here also, and it would have been fine. Okay. Yeah, that would have been east of south, but 45 degrees, it really doesn't matter. But yes, you're exactly right. Okay. So does everyone agree with a free body diagram? Could we have gotten to that point on our own?
Yes.
Hopefully. Okay. Let's break down this vector now. So this is F applied X and F applied Y. Uh-huh. Okay. Let's go ahead and solve for F applied X and F applied Y. For X, we should use which one? Cosine. Good. So for X, we'll use 90 times cosine of 45. For Y, we'll use 90 times sine, even though it's going to be the same value. Okay, for the X component, what did we get? 63.6. And for our Y component, we got negative. Negative 63.6. And so I'll show you something, listen, I'll show you something that we need to pay attention to here. We need to really pay attention to. Let's set up our net force equation. Okay, F net, we're looking for the normal force, which is a vertical or a horizontal? Vertical. Okay, and how many vertical forces do we have? 3. 1, 2, 3. Okay, because my component of my Y force is still considered a vertical force. So let's look at this. We would take upward minus downward. So this is where we have to be careful. Since we added the negative already, we don't want to put a double negative in there, right? We want that to be going downward. So we don't want to do that 2 times. So we'd say normal force, and then we're just going to do minus 63.6 minus FG, right? We're not going to say minus negative 63.6. Does that make sense? We don't want to do double negatives there, so you just got to pay attention to what we're doing, okay? The net force here in the vertical direction, what is it? What's our net force in the vertical direction? It's not moving, right? Our object's not moving in the vertical direction. Once we break down the 90, we're done with that. We don't use that ever, again, anywhere. Okay? Okay, so 0 equals normal force minus 63.6 minus mass times 9.8. Okay. So we get our normal force to equal
1043.6.
perfect.
Thank you.
So is that normal force greater than or less than it is just if it's at rest? greater than. If it was at rest and we had no other applied forces, our normal force would be 980, right? Equal to the gravitational force. But since we have this other applied force, we see a normal force greater than that. Okay, how do we feel about that? Okay, so starting with number 4, we've got two different vectors here. 200 newtons east and 100 newtons 45 degrees south of east. We want to find the net horizontal force. Okay, so if I draw this in a free body diagram, it would look like this. 200 newtons east and 100 newtons and 100 newtons at 45 degrees south of east. Okay? I want you to understand that these two things are not connected. We don't just build a triangle right here and think that's going to be okay. That's not how it works. Okay? These are two completely different vectors. So that's why I think it's best to just draw them separately when we're trying to find this vector addition. Okay? So our first vector is 200 newtons east, which means the x component here is what? 200. Good, 200, and the y component is 0. Okay, because this vector is purely horizontal. Purely. Okay? For our second vector, it's 100 newtons, 45 degrees. So this would be F2x and F2y. Okay, and these are both going to be the same value, right? Because it's a 45-degree angle. So F2x, what did we get? And F2y is equal to? Negative 70.7. Okay, here it asked for just the net horizontal force. So what's that mean we need to do? Yeah, we're just working with the x. Are they both going in the positive direction? Yes. So all we're doing is saying Fx equals 200 plus 70.7. That's it. That's it. Okay, if we wanted the net overall force, then we would have to add the y components, and then we would have to build a new triangle based off of those. Okay, but here they just asked for the net horizontal force. That's it. Okay, so this was just vector addition. This didn't really get into our free body diagrams, and it didn't talk about our normal force and things like that. Okay. Do we feel pretty good about that vector addition? Yeah? Okay. Let's try number 6 on your own. Okay, I want you to do number 6. All right, let's look at our vectors for this one, okay? Our first vector should look something like this.